Section 6.10 Specific wind turbine performance calculations. Section 6.10.1 Some aerodynamics. We need to find out how wind turbines extract energy from wind. An airfoil, whether it is the wing of an airplane or the blade of a windmill, takes advantage of Bernoulli's principle to obtain lift. Air moving over the top of the airfoil has a greater distance to travel before it can rejoin the air that took the shortcut under the foil. That means that the air pressure on the top is lower than that under the foil, which creates the lifting force that holds an airplane up or that causes a wind turbine blade to rotate. A rotating turbine blade sees air moving towards it, not only from the wind itself, but also from the relative motion of blade as it rotates. The combination of wind and blade motion is like adding two vectors, which the resultant moving across the airfoil at the correct angle to obtain lift moves the rotor along. Since the blade is moving much faster at the tip than at the hub, the blade must be twisted along its length to keep the angle right. Up to a point, increasing the angle between the airfoil and the wind improves lift at the expense of increased drag. However, increasing the angle of attack too much, that results in a phenomenon known as a stall. When a wind stalls, the airfoil over the top no longer sticks to the surface, and the resulting turbulence destroys lift. When an air climbs too steeply, stall can have tragic results. Figure 6.32 shows the idealized power curve. No power is generated at a wind speed below Vc, which is cut-in wind speed. At the wind speed between Vr and Vf, the output is equal to the rated power of the generator. When the wind speed is above Vf, the turbine is shut down. So the Vr is called the rated wind speed. The Vf is called the flaring or cut-off wind speed. The rated wind speed. For pitch-controlled turbines, an electronic system monitors the generator output power. If it exists specifications, the pitch of the turbine blade is adjusted to shade some of the wind. For stall-controlled machines, the blades are carefully designed to ultimately reduce efficiency when winds are excessive. Cut out wind speed. For pitch-controlled and active stall-controlled machines, the rotor can be stopped by rotating the blades about their longitudinal axis to create a stall. For stall-controlled machines, it is common on large turbines to have a spring-loaded rotating tips on the end of the blades. Section 6.10.3 Optimizing rotor diameter and generator rated power. For lower speed wind, increasing rotor diameter while keeping the same generator shift the power curve upward so that rated power is reached at a lower wind speed. For high-speed wind, keeping the same rotor but increasing the generator size allows the power curve to continue upward to the new rated power. Section 6.10.4 Wind speed cumulative distribution function. The total area under a probability density function curve is equal to 1, and the area between any two wind speeds is the probability that the wind is between those speeds. Therefore, the probability that the wind is less than some specific wind speed v is given by the probability of the v is less than v is equal to the cumulative distribution function, which is equal to the integral of 0 to v as the probability density function of wind speed multiplied dv. Clearly, Fv is equal to the probability when wind speed is less than v. We can get the Weibull function. The probability density function of Weibull function is equal to k divided by c multiply v divided by c exponential k minus 1 multiply e and minus v divided by c exponential k. The cumulative distribution function for Weibull statistics will be equal to the integral of the Weibull function multiply dv. If we let x is equal to v divided by c in exponential k, so that dx, the partial derivative of dx to dv, will be k multiplied divided by c multiply v divided by c k minus 1. If we appoint fv is equal to, since fv is equal to the probability v less than v is equal to 1 minus e minus v divided by c k. For special case of Rayleigh statistics, when k is equal to 2, therefore the c is equal to 2 multiply the average of wind speed divided by square root pi. So the cumulative distribution of v, the wind speed v less than v, is equal to 1 minus e minus pi divided by 4 multiply v divided by average v multiply square. So this is important. We show the probability of wind speed is less than a specific v value should be equal to 1 minus e multiply pi divided by 4 multiply the v divided by the average wind speed, the square. Section 6.10.5 Using real power curves with Weibull statistics. Figure 635 shows the power curve for 3 wind turbines. The NEG Mekong rated power is 1500 kilowatt. Rotor diameter is 64 meter. The NEG Mekong 1054 and the Vestas V42 rated power is 400 kilowatt and the rotor diameter is 42 meter. Notice how the rounding of the curve in the vicinity of the rated power make it difficult to determine what is an appropriate value of the rated wind speed VR. As a result, the rated wind speed is used less often these days as part of turbine product literature. With the power curve in hand, we know the power delivered at any given wind speed. If we combine the power at any wind speed with the hours in the wind blows at that speed, we can sum up the total kilowatt-hour of energy produced. If the site has data for hours at each wind speed, those would be used to calculate the energy delivered. Alternatively, when the wind data are incomplete, it is customary to assume Weibull statistics with an appropriate shape parameter k and scale parameter c in order to calculate the total energy produced in this area, produced by this wind turbine. Section 6.10.5, using real power curves with Weibull statistics. The legitimate question is, what is the probability that wind blows between V minus delta V divided by 2 and V plus delta V divided by 2 on a probability density function? This probability is the area under the curve between V minus delta V divided by 2 and V plus delta V divided by 2 as shown in figure 636a. If delta V is small enough, a reasonable approximation is the rectangular area shown in the figure 636b. This suggests that we can make the following approximation. The probability of V between V minus delta V divided by 2 and less than V plus delta V divided by 2 is equal to the integral of V minus delta V divided by 2 to V plus delta V divided by 2 FV multiplied dV is approximately equal to FV multiplied delta V. The FV is a probability density function and delta V is the small change size. Example 6.14, discretizing FV for wind side with a relay wind having average speed V average is equal to 8 meters per second. What is the probability that the wind would blow between 6.5 and 7.5 meters per second? How does this compare to the PDF evaluated at 7 meters per second? If we use equation 6.57, we can obtain the probability P above 6.5 should be the exponential pi minus pi divided by 4 multiply the average wind, the V 6.5 divided by the average wind speed 8 multiply the square and equal to 0.59542. The probability V above 7.5, that is equal to 0.50143. So the probability that the wind between 6.5 and 7.5 is the probability of these two minus each other. So that is equal to 0.094. From the 6.45, approximate the probability that the wind is at 7 meters per second is to be, if we use the probability density function, Fv is equal to pi multiply V divided by 2, the average the average wind speed square, E minus pi divided by 4, and this is a V divided by average V square. Therefore, if we substitute in this equation, we can obtain the probability that the wind is at 7 meters per second is 0.09416. So there is only 0.2% higher than the correct value of 0.094. From the example 6.14, we can use the wind deviation coefficient under the wind speed integral value to represent the probability of wind speed. Combining power curve data from turbine manufacturers with appropriate wind power statistics is a direct way to estimate annual energy production. This is the easiest way to do with the spreadsheet. Section 6.10.6, using capacity factor to estimate energy produced. One of the most important characteristics of any electrical power system is its rated power. Since power systems, especially wind turbines, do not run at a full power all year, they put out something else less than that maximum amount. The capacity factor CF is a convenient, dimensionless quantity between 0 and 1 that connects rated power to energy delivered. The annual energy power is equal to the rated power PR multiply 8760 multiply capacity factor. The capacity factor therefore equal to the actual energy delivered divided by the PR multiply 8760. So another way to express it is that since the annual energy delivered divided by 8760 is equal to the average power, so the capacity factor is also equal to the average power divided by the rated power. Now we complete the section 6.10.